Okay, we are live. Yeah, so as I was mentioning, today we're going to be talking about EVs and the grid. This is actually the area that I kind of do the most research, so it's near and dear to me. So we've talked a lot about aspects related to the vehicle and aspects related to charging infrastructure. But when we think about some of the fundamental questions about impacts, right, on the operation side, there's this question of what actually happens when you plug in your EV. Okay, so before we dive into addressing this particular question, we're going to do kind of a high-level overview of a sort of totally different area, which is the electric power grid. One of the challenges of kind of working in the space where you're kind of integrating now this overlap between transportation and electricity is, we also have to have kind of at least a base level of knowledge of the way this totally different sector works as well. So we're going to cover that today. Electric power grid. Typically, we divide this into three main areas. You've got generation, transmission, and distribution. So generation is just the power plants that actually produce electricity. The transmission system, these are like when you're driving along the freeway and you see those big metal towers, right, with the huge wires. That is the transmission system that transports electricity over long distances. And the last one is our local distribution system. This is like the wooden telephone pole wires and then all the like little green neighborhood transformers that you see. That's all part of the localized distribution system where stuff from the transmission gets brought to a substation and then distributed out to like a local neighborhood or city type of scale. Okay, so we're gonna talk first about kind of the generation piece. Okay, and so one of the nice things actually that we can draw on is what we've learned from electric vehicles about how electricity actually gets generated. Remember, the way that we generate electricity in the vehicle is through a generator, right? So if you have, remember that whole deal with a spinning magnet in a magnetic field, moving a coil inside of a magnetic field, that's essentially the way that the vast majority of electricity is generated. So we have turbines that are connected to generators. So as long as you can get something to spin, you can essentially produce electricity. And nearly all electricity in the world is produced this way, right? So whether you're talking about coal or natural gas or nuclear or wind or hydro, all of that is basically spinning a turbine. The only one that is going to be kind of an exception to that is solar. So I thought it might be a little bit interesting. We can do kind of a really high-level overview of some of the different power generation methods, just so that you can see that kind of at the end of the day, all of the electricity is basically made by spinning this turbine. So the first one that we'll look at, this is a steam turbine, most commonly employed in coal plants. So you have kind of the most useful diagram over here is on the right. You've got this schematic of a coal plant where you have coal that gets pushed into a furnace that gets combusted, and then you have this loop of hot water that gets turned into steam. The steam spins a turbine, which powers a generator to produce electricity. In order to complete a thermodynamic cycle, remember, we talked about thermodynamic cycles with our gasoline engines. You remember that 4-stroke diagram. Thermodynamic cycles means that you have to return to your original state so that you can resume going through the cycle. So after the water passes through the turbine, it gets condensed back into water before it gets sent back through the furnace to heat up and sent through the turbine. That thermodynamic cycle is known as a Rankine cycle, and you can see the diagram of the efficiencies here. So the Rankine cycle is about 35% efficient in practice. So if you think about the energy content of the coal turning into electricity, about 35% of that energy content is actually what gets generated in electricity, and the rest is lost as heat. Okay? You have a separate loop here that cools the water, and so you have these cooling towers. So if you ever see a coal plant, you'll see these cooling towers where that's actually safe to breathe. It's just like hot water vapor coming out of it. And then you'll also have this chimney stack, which is combustion byproducts, which is not safe to breathe. Yeah, and this is where all of the byproducts of coal combustion come out of, essentially. Okay? So that's a typical coal plant. For a natural gas plant, which is the largest electricity producing source in the US, not in California. Well, actually, it's getting close in California. Some of the renewables, gas might still be the largest, but everywhere else in the country, on average, gas is going to be kind of the dominant electricity producer. Works a little bit differently in mechanics, but in principle, it's about spinning a turbine, spinning a generator, producing electricity. You have air coming in through this nozzle. It gets compressed to high pressure. Gas gets injected in the middle segments. And then you have combustion happening, which is the thing that actually spins this entire turbine. And out of the back, you have these hot exhaust gases. This thermodynamic cycle is known as the Brayton cycle. It's a little bit more efficient, about 40%. And so natural gas turbines, with just this part of it, are more efficient than coal turbines. Does this turbine look familiar to anyone? Does this look like anything you might recognize? Yeah. Yeah, so this is like a jet engine, right? And so actually a jet engine is literally just a gas turbine. So you could actually take a jet engine, rip it off, put it into a power plant, and it would work exactly the same. Yeah, and so gas turbines can be used, the thrust out of these are strong enough to fly planes, which is why we use them that way. But in power plants, we use them to generate electricity. Note that the byproduct of this is like extremely hot gases, right? So one of the things you can do with a gas turbine is take those hot gases and literally throw it back into a Rankine cycle where you are boiling water. And so a lot of natural gas power plants do this process where you have both the Brayton cycle as well as a steam turbine. So you can see this diagram on the right that shows that happening. So here is the Brayton cycle from the natural gas turbine, and then the hot exhaust gases are used to heat up water, boil water, turn it into steam, go through a steam turbine. And so you have two separate turbines that are doing different processes. And combined, this is known as a combined cycle plant, you have actually much higher efficiencies, right? So here, we're talking on the order of like 60% efficient, rather than like a 35 to 40% efficient. But at the end of the day, it's all about spinning this turbine to produce electricity from a generator. And you guessed it, for a nuclear plant, it's basically the same thing. This sort of simple schematic of a nuclear plant is going to look essentially the same as a coal plant. If you look at the right-hand side, you've got a turbine that spins from steam going through it, and then it gets condensed back into water, cooled down through an external reservoir. But the thing that heats up the water in the boiler is not coal combustion. It is essentially a nuclear fission reaction. And so you have in your containment structure in the nuclear reactor, you have uranium that is undergoing fission in order to generate heat. That heats up water in another separate containment loop that then heats up the water in the boiler. So if you swap this thing out for coal combustion, you've got a coal plant, and then if you throw in this nuclear reactor that heats up water, you've got a nuclear plant. There's obviously a bit of simplification happening here, right? The implementation of this can be relatively complex, but on the actual electricity production side, it really is not so different from a coal plant. Okay, any questions about any of this so far? No? Okay, so other ones to look at. Wind turbines. Maybe this is the easiest to visualize. You can actually see the mechanics of the turbine spinning from external forces coming in. So instead of heating something up, this is naturally from wind blowing through the turbine. There's a maximum theoretical efficiency of about 60%, but in real world terms, we're usually capturing about 35 to 45% of the kinetic energy of the wind. These turbines can get really big, and you'll notice if anyone has ever seen one from a distance or actually been to a wind turbine, these things are enormously tall, right? And one of the reasons for that is actually wind speeds tend to be higher at slightly higher elevations above the ground. So we want that height to capture some of the faster moving wind speeds. And these things get really big, okay? So the diameter of one of these turbines can be larger than a football field. And in fact, some of the wind turbines that they put offshore, so those are the ones like out in the ocean, those tend to be even larger. And so those could be, the length of like 2 football fields, for example. But again, spinning, getting the turbine to spin, you provide rotational energy in your generator to produce electricity, really kind of the same mechanism here. Okay, and then kind of the last one for these series of different turbines, so hydro. So these are hydroelectric dams. Instead of like the kinetic energy from wind moving, this is exploiting the potential energy difference between things at high elevation and things at low elevation. So water has a tremendous amount of potential energy due to that elevation difference and the mass of the water. And the amount of energy that you can get is kind of dictated by the differential in height between the top and the bottom of the dam. This is a sort of set of diagrams of different types of turbines that are employed at dams around the world. And the design of these are meant to accommodate slightly different attributes of your dam system. And so depending on the height, depending on the flow rates of the water, and the overall size of the dam, all of these things will influence kind of the design of the turbine. But again, main thing is getting that turbine to spin to generate electricity. So we can see in the power system, we are kind of exploiting this idea of how we generate electricity. It really is not that different from the generators that we've talked about in electric vehicles themselves. And we use the ability to generate rotation in the turbine to correspond to moving the generator in such a way that we can produce electricity. There are exceptions to this, and probably the most prominent one is solar power. Okay, and so the way that a solar panel works is not by creating movements. Here we have sunlight hitting the surface of a photovoltaic panel. There are differences in charges on the surface of the panel, and light hitting it is enough to perturb the surface enough to essentially release electrons to generate a current, because the electrons kind of want to go to the opposite side. So solar photovoltaic panels are probably the most widespread difference. They also produce current in DC as opposed to AC. AC is the type of power produced by generators. And here, if you want solar power to participate in the broader grid, they need a converter to go from DC to AC before they can inject their power onto the grid system. Okay? The other piece that I want to cover as it relates to the grid is having to do with impacts. I think one of the main motivations for thinking about how electric vehicles integrate with the grid is understanding the emissions impact on the operational side of things. You may have seen articles or research studies about whether or not gas cars are cleaner or dirtier than EVs. We've talked about, on the manufacturing side, kind of what that looks like, right? But what we haven't covered yet is the actual operation, right? And so for a gas car, we can measure the emissions coming out of the tailpipe, but it's a lot harder on the electric vehicle side, because how do you determine what power is responding to an electric vehicle getting charged? So this portion, we're going to look at the general types of emissions and their implications. So combustion emissions, we think about when fossil fuels are combusted, we categorize them into two broad groups, right? This is something I've talked about before in this class. We have greenhouse gases and local air pollutants. Greenhouse gases are things that strengthen our greenhouse effect and lead to climate change. And there are a whole bunch of impacts related to that. And then you have local air pollution, which are emissions that lead to lower air quality and thereby are associated with negative health outcomes, right? So things like incidence of asthma, lung disease, cardiovascular diseases. All of these can be compounded by local air pollution. So carbon dioxide, that's kind of the big one that we usually talk about with greenhouse gases. This is where CO2 accumulates in the atmosphere and it acts as a greenhouse gas, which means that it traps heat within Earth's atmosphere. This diagram here shows this kind of equilibrium where you have sunlight energy coming in and then irradiating back out into space. And what carbon dioxide does is it disrupts this equilibrium in such a way that heat is trapped for a longer period of time, and it's harder for it to escape into space, which leads to global increases in temperature. And so from an empirical perspective, we're able to measure this, right? And so this is the relationship between global mean temperatures and carbon dioxide concentrations over time. So what you can see here on the right-hand side is CO2 concentrations increasing. This is the mean measure of CO2 concentration annually over time. And this increase is really due to anthropogenic or man-made contributions of carbon dioxide. And as that has gone up, we have seen global temperatures increase every year as well. Okay, any questions about this? Yeah, so this is super high-level overview of climate change. We're not going to get so much into detail. We're going to kind of less on the effects and go back to thinking about the pollutants themselves. So carbon dioxide is definitely the most prevalent greenhouse gas. That's the one that we're kind of most worried about. But there are other greenhouse gases that contribute to global warming. And some of the more prominent ones you can see in this table on the right. So the other two being methane and N2O. These are also commonly used, so methane as a fuel, so that can leak, and then also as combustion byproducts. This table is describing the relative effect compared to a baseline of CO2. So basically the idea is that like, if I emit a molecule of CO2, that leads to some amount of warming. If I emit a molecule of methane, that leads to a different amount of warming. And methane actually is many times, will lead to a much larger amount of warming than CO2. And so in one of the more recent measurements of this, they're basically saying methane is about 30 times worse than CO2, and N2O is about 200 to 300 times worse than CO2. But CO2, there's a lot more of it. We just need to be careful with these. And also there's a difference between the 20-year and 100-year time span that you look at the impacts, because CO2 stays around for a lot longer in the atmosphere, whereas the other ones degrade a little bit faster. So that's one thing to note in the difference. So yeah, from a greenhouse gas perspective, CO2 is the biggest. There are a couple other ones, and we kind of care about everything. This is just a way to put everything in the same perspective. Okay, types of air pollution. So this is referring to the local air pollution that's damaging to our health. So you've got things like carbon monoxide, lead, nitrogen oxides, ozone, particulate matter, sulfur dioxide. So we're going to go through a bunch of the more significant ones, talk about some of the implications there. Carbon monoxide, this is a colorless, odorless gas resulting from incomplete combustion of fossil fuels. So this is a very common byproduct of any form of combustion. Anytime you have incomplete combustion, you're probably producing carbon monoxide. This is like the reason why you don't run your gas car inside of a enclosed space like in a garage, right? Because that leads to a buildup of carbon monoxide, which can be very deadly. Carbon monoxide, so for those of you who have taken some biology classes, it is, so in your red blood cells, you have hemoglobin, which transports oxygen around. Carbon dioxide binds to hemoglobin it replaces the spot that oxygen would normally occupy, and it binds a lot tighter, so it doesn't release it, so you basically can't breathe if you have carbon monoxide poisoning. So yeah, pretty bad stuff. And again, any combustion process is likely producing carbon monoxide to some extent. Nitrogen oxides. This is a family of gases formed by combustion at high temperatures. I believe I've mentioned this before, right? If you have combustion in the presence of air, which is majority nitrogen, you can be producing nitrogen oxides if the combustion is happening at high enough temperatures. So this often appears as like a brownish gas. This is oftentimes one of the things that we find in smog and also acid rain. It's got lots of bad health outcomes associated with it: asthma, heart disease, diabetes, poor birth outcomes, and even increased mortality rates. There have been, it's bad enough that regulations like the Clean Air Act have helped to target and reduce the amount of nitrogen oxide, and so you can see that here. NOx in the US has decreased substantially over time, both in part due to specific requirements to scrub NOx out of combustion byproducts, but also in general, like a reduction in coal usage over the last like 20 years or so. You can see there's a particularly bad spot in California. This is in the Los Angeles area. Yeah, there's enough kind of heavy-duty vehicle usage that concentrations of NOx in like Los Angeles, the greater Los Angeles area, have remained pretty bad over time. Any questions? Okay. Sulfur oxides, similar type of story with NOx. If you have any sulfur in your fuel, this is a very common product to have, right? So sulfur in your hydrocarbons, you might think of this kind of as an impurity essentially, and so the presence of sulfur impurities leads to the formation of sulfur oxides when you combust it. The main source of this is coal, right? Sulfur is a pretty common compound found in coal. This is a very common precursor to acid rain. It's harmful to your respiratory system and can also react with other compounds to form particulate matter. At high concentrations, yeah, this can be damaging even to the surface of biological materials like plants. Similar type of story here. The big decrease in sulfur oxides is thanks to a sort of phase out of coal in this country. And so this is what high concentrations of SOx looks like in the mid-2000s compared to a couple years later. As coal usage decreased quite a bit, we can see that in general the concentrations are a lot better. Okay, and the last one that I'm going to talk about is particulate matter. So I alluded to this before, I think in the previous lecture when we were talking about heavy-duty vehicles. Particulate matter is, the big kind of killer, right? So this is the stuff you really don't want to be breathing. It's a mixture of different solid particles and liquid droplets in the air. And I have this diagram to kind of give a sense of scale for you guys. So the big the big blue dot, that is particulate matter 90. The number coming after the PM refers to the size. So PM 90 refers to something about 90 micrometers or less, right? And so that would be the equivalent of like a grain of sand. PM 50 to 70, so 50 micrometers up to 70 micrometers. That is about the width of a human hair. And then you have PM 10. This is a pretty common like environmental sort of not byproduct, but something that you would experience or be exposed to kind of normally. So this would be dust, pollen, mold. That's usually going to be at the size of PM 10. PM 10 is about the limit of your body's system to handle. So when we breathe air, right, and we're ingesting PM 10, a lot of that's going to be captured in our nose and in our snot, right? That size is essentially what our body is able to handle. So smaller than that, and then you're starting to get into problems, right? So these little white dots, that's PM 2.5, and that is coming from soot and pollution byproducts. So this is very, very fine particulate matter. That's going to go straight through all of your protective barriers. So the hairs in your nose and your snot, that's not really going to be able to stop much of this. So PM 2.5 can settle into your bronchi and in your lungs, and lead to all sorts of health issues. They're often considered carcinogens, and it's known to essentially account for a massive amount of mortalities worldwide. So we estimate something on the order of like 4 million deaths annually, basically from PM 2.5 exposure. It's the 5th leading risk factor for death. And generally speaking, the dirtier your combustion process is, the more particulate matter is being emitted. And this pie chart down here is kind of a smattering of different PM 2.5 particles. These are not, these PM 2.5 is not like a homogeneous particle. It can be comprised of many different things, and so there's a couple of examples of compounds that are present in PM 2.5. Okay, what does that look like in the U.S.? This chart is a little bit outdated, but relatively speaking, is probably going to look not so different from today. Some places might be a little bit cleaner, but this is essentially the relative amounts of PM 2.5 concentrations in the US. Okay, and anywhere that you are doing combustion, you probably have at least some amount of PM 2.5 happening, and the dirtier it is, the higher the concentrations of PM 2.5. Any questions? So one of the things you guys are probably noticing from the way these maps are displaying is that the distribution of where pollution is happening is actually pretty different across our country. And one of the reasons for that is, if we think about one of the big sources of pollution coming from power generators, that is not something that is sort of evenly distributed across the country. So this is a figure that shows all of the power plants in the US, all of the what we'll call kind of wholesale power producers. So this doesn't include things like local diesel generators or like rooftop solar. These are basically power plants that are feeding into our main electricity grid. And what you'll see is a pretty sort of different distribution of power sources. So things to watch out for on this figure. So you've got all these dots. The color of the dots correspond to the type of power plant, the fuel type. So you have blue for coal, green for hydro, purple for natural gas, orange for nuclear, and then solar in pink. And then the size of the dot corresponds to how big the power plant is, essentially how much power it can produce at its like peak capacity. So a couple trends to notice. So you'll see like in the state of California, for example, you won't find any blue dots, right? Coal power plants are not allowed to operate in California. In the Pacific Northwest, you have a lot of big green dots, and those are hydro facilities. Oregon and Washington are kind of well known for having a lot of their power coming from hydroelectric dams. Ideally, we could do that everywhere, but that is more of a resource-constrained power generation unit. You have to locate them on essentially these bodies of water that may not exist everywhere in the country. In the Midwest, you'll see a big swath of gray, and those are our wind turbines. It just so happens that that the middle of the country tends to have much higher wind speeds, and so those are kind of the best places to deploy wind turbines. And then on the East Coast, right, much higher density of power plants, generally corresponding to higher density of people. And you'll notice a lot more blue dots corresponding to coal plants in the sort of eastern half of the country compared to the western half of the country. And that's kind of reflected, right, in this distribution of particulate matter, in the SOx distribution, and in the NOx. A lot of that is, coming from coal, and to some degree, the NOx also from natural gas. The last thing I'll mention, orange dots. You see a lot of them all over the place. There's only one in California. Does anyone actually know what nuclear plant that is pointing to in California? It is close to Santa Barbara, and it's actually in San Luis Obispo. It's the Diablo Canyon power plant. It's the last nuclear power plant in California. It was actually slated to be retired last year, but the legislature re-upped it and decided to keep it operating. So we still have one nuclear power plant operating in the state of California. Okay, so you've got a bunch of power plants everywhere. And let's say, okay, I live in Davis, and I can't really zoom in on the slide here, but you can imagine I plug in my electric car, there's all these power plants located around me. Which one is actually responding to me plugging in my car to charge it, right? Because that's what's going to tell me information that I'd be interested in about thinking on the operational aspects of the vehicle. So we're going to do a little game right now so that we can get a better grasp and understanding of how the electricity system actually operates. So this is called a dispatch game, and this is meant to emulate essentially the way that power plants actually operate in the country and actually kind of all around the world. So, okay, I think the way that we're going to do it, we'll just do it by table. I know some tables only have one person, but you'll just be your own. You'll be your own power plant, and then for any tables with more than one person, you guys will act as one power plant. So you guys all are going to get assigned a power plant, and you get 3 bits of information. You get power, which is the amount of capacity that you have. You'll have a corresponding fuel price. So the fuel price tells you how much it costs you to produce power, and you'll and just kind of as a side info, it'll tell you the fuel type. Okay, so the goal in this game is to make as much money as possible. okay? And the way you make money is by selling power that you produce. So you produce electricity, and you're going to sell that. So no communicating with other tables. We're going to have anti-monopoly rules. And the way this is going to work is I'm what is known as the independent system operator, the ISO. This is the entity in charge of turning on power plants in order to meet load demands. And by load demands, I mean basically requests for electricity. So we have one in California called California ISO or CAISO. And then there's ISOs kind of all around the country that operate in a similar manner. And I basically am going to choose from you guys which power plants I want to turn on. So this is the way it works. So at the bottom, I've got a link. You guys can go ahead, go to that link, and you should be able to choose a power plant. It'll just give you a randomly generated power plant. So what I want you to do is essentially to write down on a piece of paper your bid into the market. So the way a dispatch works is through an auction. I have to provide X units of electricity to fulfill all demand, and I'm going to choose to turn on power plants to provide power to me based on the cheapest price. So basically, I'm going to turn on power plants one at a time from lowest price to highest price. So if someone bids in $1, I say, okay, I'm going to turn you on first, and then someone bids $2, then I say, okay, then I'm going to turn you on next, all the way until I have enough power to get what I need, right? And so the lower you bid, the more likely you are to get turned on. But you do have a fuel price to keep in mind. Okay, this is the most important part of it, which I think a lot of people might get confused on. Once I've fulfilled all the demand, everyone who turned on gets paid not based off of what you bid, but based off of what's known as the clearing price, which is the highest bid that was turned on, right? And so if the last person that I turn on bid at $10 and you bid at $1, you don't get paid $1, you get paid $10, okay? So there's some strategy here to think about. Okay, so is the link working for everyone? Okay, and everyone's got a power plant. Go ahead. You can, if there's multiple people, you can discuss. Otherwise, think strategically about what you think your optimal bid should be to make as much money as possible. I'm going to give you guys a minute to think about it, and then we will run our dispatch. All right, everyone ready? Does anyone need more time? Okay, so we're gonna start our auction. So, who bid in $0? Anyone? No one bid in $0. Okay, $1, $2, $3, $4, $5. Okay. What can you tell me? Tell me all of the information on your sheet. So, what fuel type? Solar. What's your capacity? 350. And how much does it cost you to produce? Zero. Okay, great. All right. Anyone at? Oh, you're at. Well, are you? Did you bid at 0? Okay. I'll put you in here. Okay. So what do you have? Solar. How much capacity? 200, and your fuel cost is 300, and your fuel cost is 0. Great. Did anyone bid in at $10 or below? Okay, what did you guys have? Okay. What fuel type? Hydro. Capacity? 700. And your fuel cost is 0? 601? Okay. Okay. Anyone else at 10 or below? Yeah. Okay. And 0 for cost. Great. Okay. Anyone bid in at 15 or below?
Yep.
2. Okay. So, 3. Okay. What did you have?
Hydro,
Okay.
400 megawatt capacity,
Yep.
and bid in at $12.
Oh, what was your fuel cost?
$9.11.
Okay.
And we were hydro
Hydro.
at 800 megawatts
800.
and $10.11.
10, 11. Okay. Actually, you know what? I will put in people's bids. 12. What did you guys bid in at? 11. 8. Bid in at 0. And you guys bid in at 5. Yeah. Okay. And then, did you also bid in below 15?
Yeah.
Okay. What did you tell me about your thing?
Name?
The fuel. Sorry, what was the fuel type? What was your fuel type? Did you get assigned a generator?
No.
No. Okay. All right. We'll skip. Anyone else? No. Everyone gets one power plant. Okay. Oh yeah. Did you?
Hydro,
Okay.
400 megawatts,
Hydro, 400.
and $8.44.
What was it?
$8.44.
And what did you bid in at?
12.
12. Okay. Okay. Anyone bid below 20? 3. Okay. 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 And what was your cost? And 17 what? 21. Great. Sorry? 10? You bid in at 10, you mean? Okay. And what was your nuclear? Okay. 3,500. And fuel cost? Yes.
Nuclear.
Nuclear,
5,000.
5,000.
1920 and 15.
Okay.
Yeah.
It could. Yeah, so in fact, if I rearrange this order, so let's see, based on okay, so let's say I needed only 10,000. So here we go. This is 6825. Okay. So let's suppose that I only needed to satisfy 10,000 megawatts of capacity. So the way that I would do it is, this is not quite in order, but it's almost in order. I'm going from lowest bid to highest bid. So I would do solar first, the row 3, because they bid at 0. And then row 2, bid at 5. I would turn both of those on. Then I would turn on the power plants that bid in at $8. Then I would turn on the one who bid at $10, $11, $12, and then finally $15. And then I have enough. And everyone else who bid higher than that, you don't get turned on. Okay? So let's see how much money people made. So the way we're going to do that is our final bid was $15. So we're going to do 15 times the capacity minus your capacity times your fuel cost, right? So you make money from selling electricity at that clearing price, but you lose money from producing electricity at a particular fuel price. Oop, what does this say? Okay, so everyone up here, and then let me just see again. So this was 6825, so 3,175. The last plant doesn't turn on all the way. It's equal to 3,175 times fuel cost, times our bid, which was 15 minus 3,175 times the fuel cost. Okay, so everyone made money except, unfortunately, our 2 nuclear plants who both bid in at a loss, at a price lower than your fuel cost, which means that they both lost some $12,000, $13,000. Yeah, sorry. Unfortunately, not the optimal bid price. So, does anyone see, can anyone think about what the optimal strategy would be to bid in? It's not 0, right? Because if, let's say, the nuclear plant bid in at 0, they would have lost even more money. So it could be above your fuel price. So there's actually a couple examples of this. Both of these examples bid in at 12 and 11, actually here as well, right? So all 3 of these bid in at prices above their fuel cost. And in this case, it paid off. They were still turned on. They didn't lose money because the final bid ends up higher than their fuel price. And in fact, they couldn't ever lose money to some degree because they're being conservative with the bid relative to the fuel cost. But you're putting money on the table here. And why is that? You could bid lower, right? So think about this. Let's say that the final clearing price was $10.50. Okay? That means none of these three generators would have turned on, right? Because their bid price was higher than the clearing price. But if it was at $10.50 and they did turn on, they would have made money. Okay. So it turns out the optimal strategy is to actually bid in at your operational cost, right? And so think about what that means. It means if I bid in and I happen to be the last generator, then I break even, right? Because what I get paid is the same as what I bid. But if the bid is ever higher, then I will be making money. I'm guaranteed to make money because I bid in at the break-even price. And I haven't lost any opportunity if the bid ever gets any higher. Okay.
Well, I made 4,500.
Yeah.
Even if we had zero, I would have not made no money, but I would have always got turned on.
Yeah, exactly. So it's a little bit easier for renewables. But yes, so this is the way that our electricity system operates, right? We have a bunch of power plants, and to make sure that we as consumers pay the lowest amount of money for electricity, it's done in this way so that we are dispatching or turning on power plants at the lowest power production cost possible. Okay? So you can actually, let me jump back to the slides. So you can actually generate what's known as a dispatch curve, where we order all of the power plants in our system from left to right based off of how expensive it is to produce electricity. And so that curve ends up looking something like this. It's the same kind of diagram schematic where the dots represent the fuel type, and then it's like the cumulative amount. And so if I needed like 50 gigawatts of capacity, I would turn on this guy, this guy, this guy, this guy, this guy, all the way up to here. And if I needed more, I would continue turning on power plants in this order. So the generators that turn on, we turn on from left to right, and then what gets paid is the price of the last generator. Okay? And note that every additional megawatt is more expensive than the previous megawatt, and that's how we build up this marginal cost curve. Actually, I have one last question for you guys regarding this dispatch game. Let's suppose I, as the operator, needed to turn on every single generator to meet demand. Okay? The power demand is so high, it's like a really hot day, everyone's turning on their AC. So you guys, all of you guys as power plants, I'm just gonna go through our same system and I'm gonna dispatch everyone in the same way that I just did. So the optimal strategy for all of the generators, right, is the same. You wanna bid in at your fuel price, except for the last generator. What is the optimal strategy for the last generator? Yeah, we bid way, way up, right? So it's not like this in every country in the world, but in most developed countries, the way that the power system operates is demand must be met, okay? people hate blackouts, right? The idea that our power system would ever do what's known as load shedding is really kind of a last resort thing, right? There are actually other countries where load shedding or essentially turning off power to certain places is not uncommon. So like in India, for example, there's certain regions at like certain times of the day, they just turn power off. And that's the way that they manage their power system. We don't do that in the US. That would be, heads would roll, politicians would get fired, utility companies would go bankrupt. And that's happened before. So you have to meet the demand. And if you have to meet the demand, then the supplier, if there's no one else to take, can go really extreme, right? So whoever has the most expensive power plant in this room, you could bid like $10 trillion. And technically speaking, in the way that we've designed the system, I would have to take it because I just have to meet demand. So in reality, when we're getting to this portion of our dispatch curve, you'll notice that the prices are much higher. They can't literally bid an infinite amount of money, right? That would just destroy the system. There's actually a price ceiling in the electricity market to prevent these types of things from happening. Okay. So all of that is, all this stuff that we've been talking about is building up the foundation to now think about our original question of, what happens when I actually plug in my car to the grid? So let's take a look at real dispatch of electricity, an example of this. So this is, this is coincidentally also known as a dispatch curve. It's a little different from the dispatch curve I was just showing. So forget the colors for a second and the fill, and just take a look at this shape. So these fluctuations, the total amount here, that is electricity demand, specifically electricity demand in Los Angeles area. So this is in the Southern California Edison territory, which covers basically everything outside of like downtown LA. Okay, so if anyone's from LA, you've probably gotten electricity bills and utility bills from Southern California Edison, right? And these load curves are like, okay, down here, this is the middle of the night. This is when the least electricity is being used. And then during the day, people are waking up, turning on the lights, turning on their AC, peeking out. Then people are going home. The office lights are turning off, ACs are turning off, blah, blah, blah. Go back, and then the start of a new day, okay? So this is what electricity demand actually looks like in Los Angeles. This is over the course of like a week or so, right? And so each little hump here is corresponding to the changing electricity demand over the course of like 24 hours. These two peaks are a little bit lower. Can anyone guess why that is? Weekends, exactly. Yeah, so weekend load demands tend to be a little bit lower because people aren't using as much electricity on the weekends, going to work and that sort of thing. Exactly. So if you think about the overall shape as the load demand, the colors that fill this in are the power generation units that are supplying electricity. So over the course of a day, this stuff up here, that's solar, right? And so solar is only appearing during daytime hours, and then during nighttime hours, nothing. Okay, green is wind, and then kind of this bottom big part here, that's natural gas, right? Natural gas is the flexibility in our system. It's like peaking up and down to accommodate changes in solar generation and wind generation. Okay? So that's our 1 week of dispatch, electricity dispatch in Los Angeles. So it's cheaper to transmit electricity than it is to transport fuel. And so we have power plants located all over, and then electricity can get transmitted from place to place. And this is just kind of a schematic of the major transmission lines in the US. So going back to the question about charging our vehicles, right? There are locational factors related to charging, right? If I charge my car down here in Southern California, you can see on the map, oh, I'm next to a bunch of natural gas and solar. There's some hydro and wind. If I'm charging my car over here, oh, I'm next to a bunch of ton of wind resources. But if I'm charging my car over here, like I'm next to a bunch of large coal plants, right? And so depending on the location of my charging, the impact could be different. But it gets more complicated than that too, right? Because the timing is also an important factor too. So if we take a look here, if I was charging at this line, then you'll see, oh, about half of the energy at that period of time that I'm charging is solar, right? And then some from wind and some from natural gas. Whereas if I charge from here, about half of that is natural gas. So if a car is charging in the middle of the day, the proportion of power coming from solar is substantially higher. And if the vehicle is charging at nighttime, the proportion of power from natural gas might be substantially higher. And so this effect changes both depending on where you are and when you are charging. Any questions about this? Okay, so let's do a little example where I calculate emissions from my vehicle. So this is like a hypothetical example. It's 3 p.m. in Davis, and I'm charging my car at level 2 for an hour. And let's suppose that the primary sources of energy in this area at this time are primarily coming from solar power production and from a natural gas plant. So, how the color is a little hard to read, but this is basically saying at this particular time, 90% of my electricity is coming from solar, and about 10% of my electricity is coming from my natural gas plant. So that's supplying all of the electricity demand in the area that I'm interested in. So how do I actually calculate the emissions? So for an hour at 6 kilowatts, right, the amount of energy that is produced is 6 kilowatt hours. So 90% of that is coming from solar, which has an emissions rate of 0. So 0 pounds of CO2 per kilowatt hour. And then, so that's on the contribution of solar. On the right-hand side, I have the contribution from natural gas. So 6 kilowatt hours times the 10%, 0.1, times the natural gas emissions rate, which is approximately a pound of CO2 per kilowatt hour of electricity. Okay, so I can do this math and I can figure out the average emissions rate. I didn't actually write it down here, but it's right about 0.6 pounds of CO2 per kilowatt hour. This method of calculating emissions is known as the average emissions rate. It's an attributional approach to calculating emissions. So we looked at the average power production from solar, the average power production from natural gas. Okay? Hopefully that's pretty straightforward. Everyone's able to follow along. And now let's actually do this a little bit differently. So we're actually going to use the exact same system. So on average, we're 90% solar and 10% natural gas. and then I plug in my car, right? So based off of how we played our dispatch game, what's actually happening? So think back to our dispatch game. Who do you think produces electricity cheaper, solar or natural gas? Solar, right? There's no fuel cost associated with solar. So who gets dispatched first? Solar, right? And so there's a bunch of other electricity demand besides our car, and that's getting satisfied by solar. And so the thing that is last to dispatch is the natural gas plant. So when you plug in your car, the solar is already fully utilized, right? It's fully on. There's nothing left to use because that was the first thing that was dispatched. But there's still room on the natural gas side to increase, right? So it's actually the natural gas plant that would technically be ramping up to provide you the electricity that you're putting into your car. So that changes our calculation, right? Because now we're basically saying all of the electricity is coming from the natural gas plant. And so the calculation, it's 100% coming from natural gas, and we have our natural gas emissions rate of 1 pound of CO2 per kilowatt hour, and that yields 6 pounds of CO2. So compare, this is the exact same situation, exact same scenario as the previous slide, but this emissions is 10 times higher, right? In the previous slide, it was 0.6 pounds. In this slide, it's 6 pounds. And that's entirely an artifact of how we decide to count it. So this way of calculating it is known as a marginal emissions rate, also known as a consequential approach to calculating emissions. Okay, so I've shown you guys 2 different ways of calculating emissions. Which way do you guys think is right? So raise your hand for average emissions rate. Okay, and raise your hand for marginal emissions rate. Okay, maybe some, I'm sure. Yeah, so this is not like a settled science, right? So this is more based on the way that you want to make assumptions, right? I think maybe to some degree you might think it makes more sense to do this latter one because you're saying, oh, the thing that's actually responding, which is fair. But this isn't really a settled science. This is actually still like, in some circles, still kind of heavily debated and can lead to pretty different answers. So, it is true that maybe when I plug in the car, this natural gas plant is responding. But then, when we think about all of the other things on the grid, like why is it that the lights and the fridge and our projector gets to claim the solar and the car has to claim the natural gas, right? It's about the way that we decide, we allocate who's producing what electricity to what sort of demand source. And so there's a lot of thoughts about kind of the proper ways of doing this and the situations in which it makes sense to do it on this consequential basis versus one to do it on an average basis. Right, and so if you are doing these like counterfactual scenarios where you're looking at a world with electric vehicles compared to a different world where that's changing, then maybe it makes sense to do a consequential analysis. If you're doing like retrospective studies and trying to understand the impact of electric vehicles in your system, maybe it makes more sense to do the average. But I think for you guys, the kind of big takeaway is that whenever you see studies or papers or even media articles about, oh, how clean an EV is compared to a gas car, that depends a lot on the way that people have actually approached this and how they've done the calculations, right? We can see, even in just this mini example, you can have a 10x difference in the amount of emissions. So something to keep in mind. Okay, any questions about this? Okay, so that covers the sort of emissions piece. The last part that I want to talk about today is now folding in this idea of how vehicles and grids can actually interact in more interesting ways. And so VGI, also known as vehicle grid integration, is a pretty big area of study where we think about how vehicles can actually act as assets to help with issues that the grid is facing. So wanted to provide just a little bit of context for you guys. So in California, what does peak demand look like? So I was showing you guys the shape of electricity demands in Los Angeles. You can kind of do that and extrapolate out, well, not extrapolate out, you can actually look at the data for load in California. These are plots of daily load curves from KAISO, our system operator that I was emulating in our little game. So they have this dashboard where you can look at daily electricity. And the peak demand, that is the point in the day that our state is asking for the most electricity, varies from about 25 gigawatts to 40 gigawatts, depending on what day of the year that you're looking at, right? So summer, fall is usually highest peak loads because of AC demands. And then in the lower, like winter, spring times, you might have peaks more at the like 25 gigawatts. And then in terms of energy, we consume about 700 to 900 gigawatt hours per day. Okay. The highest historic demand, I don't know if anyone was around in California back in September of 2022. If you were, you probably got a text alert that said, hey, please use less electricity. That was the highest recorded historical demand on our system of 52 gigawatts. We're getting close to our generation capacity to provide power. The other thing I want to point to is battery storage in California. We have a lot of solar. One of the ways that we can mitigate some of the grid issues is having bulk storage where you can actually take electricity from the grid, store it, and use it at times when you need it. Okay? So it's a little bit weird the way we do storage on the power system. We have about 16.9 gigawatts in terms of power. In terms of energy, these are known as 4-hour batteries, so that corresponds to something like 70-ish gigawatt hours of capacity in terms of grid batteries in our system. And for context, how does that scale to electric vehicle potential? So surprisingly, even with what we have on the road today, there are more batteries in terms of capacity on the road than there are in terms of storage providing service to the grid. Right, so we have about 200 gigawatt hours of batteries just sitting around in cars in California compared to the 70 gigawatt hours that are specifically being used for grid storage. The total power output is maybe a little bit lower depending on the way that you think about this. This is, on the power side of things, is about 15 gigawatts, assuming that people are doing level 2 charging. But still, a very sort of substantial amount of energy and power relative to what we have on the grid. And so we've talked about this idea that like most people drive maybe an hour a day. And so if your car is sitting around for 20 plus hours of the day, you know, that's potentially an asset that can be used. And so the idea here is like understanding all the intricacies and implementation of a system where the grid can actually leverage your batteries. Okay, so let's talk a little bit about how this works. So we have our normal setup. We have a car and a charger, right? So car comes in and it plugs in and charges up. And you have to receive some benefit for allowing your electric vehicle to be used. It is a nice thing, right? Think about if the 20 hours plus that you don't use your car, that you could actually get paid for it, right? That'd be a nice little benefit. And so we have to think about the whole world on the consumer side, what that looks like. And that has to sync up with, on the electricity grid, it's asking things of your battery. And so what sorts of services are needed on the electricity grid side, and how does that mesh with the benefits that an EV owner would want to receive for allowing their car to be used in this way? So I'm going to get into those two sides of it in a moment. But first, we're going to look at the sort of ecosystem to enable VGI on kind of the hardware side. So the first thing I want to talk about is kind of nomenclature, different ways that the vehicle can participate. So one, and probably the easier one, is managed charging or smart charging, also known as V1G. So that's like one directional vehicle to grid integration. So all this means is that you are charging your car at specific times. So imagine that I drive home at like 5 o'clock and I plug in my car. So normally what would happen is I get home and I plug the car in and it just starts charging. With a managed car, maybe you drive home, you plug in, there's some kind of communication and the grid tells the car in some way, actually 5 o'clock, this is not a good time for you to charge. There's a lot of other people using electricity right now. It's also going to be maybe more expensive. Let's hold off on charging. And then maybe at 9, 10 o'clock, it says, okay, this is a good time to charge. Let's start charging, right? So this is where the charging is coupled to meet times that the grid actually wants you to charge, right? And so that might be at times where more renewables are available. Maybe that's avoiding like peak times where electricity is more expensive and so on. It can also mean not just when you start charging, but also when you stop charging. So maybe your car is plugged in and prices are starting to go up, and so it says, okay, I'm gonna stop charging for now and I'll start charging again later. And there's different ways to do this. This is probably the most tedious would be like someone has to manually go in and like plug their car in and unplug. This is probably the least realistic one, right? People probably don't want to be getting a signal from the grid, going to their garage, unplugging their car or plugging their car in. It can be controlled through apps or vehicle telematics. So this is controls on the vehicle side where there's some kind of communication signal to the vehicle that it then will stop the charging. You could also have it on the charger side where you have controls from the charger, and I think this one is probably the most common, that are integrated with grid signals, and it says, oh, please, it will just not charge at certain times. So that's actually a picture of my app where you can put in your utility and then the rate structure that you're in, and it'll just not charge at times that are more expensive. So if I were to go home and plug in at like 5 p.m., nothing would happen because that's at peak times. It would wait until 9 o'clock p.m. and then it would start charging when the prices drop. Okay? So that's all V1G. And then we also have V2G or V2X as a generic way of talking about this. And so this slide is mainly to provide a distinction between different V2L schemes. So if you have a V2X, that means it's not just about charging your car. It means your car can actually discharge electricity back onto whatever system is requesting. And so vehicle to load, this is the simplest. This is where you have like a 110 plug. So there's a couple of cars that have this, and so I could actually plug in some appliance into my car, and then the electricity would just be coming from the battery from my car instead of from the grid. That's known as vehicle to load. Vehicle to home is where I can plug in the car and provide electricity into a smaller disconnected grid system. And so if you have the right hardware for this in your home, let's say there's a blackout and you had the right electric vehicle, you could just take your electric car, plug it into your like home system, and you would locally have electricity up and running for your home when the rest of your neighborhood is like blacked out. So that's vehicle to home. And then the last one is vehicle to grid. This is where I plug in my car and I can discharge electricity back onto the grid. Okay? So this stuff is more complex than smart charging and V1G. This requires more hardware. So in addition to V2G, right, or in addition to smart charging, I should say, V2G is what allows for bi-directional flow of electricity from the car back to the grid. So what does that look like in terms of hardware, software? So on the vehicle side, actually not much, right? You have a lot. We know when we charge normally, we're going from AC to DC when you're doing level 1 and level 2 charging. And so there's actually a converter in the car already, right? Because the battery going to the motor has a converter to go from DC to AC. So most of the hardware is there, and you need some additional hardware requirements. But actually most of it is actually going to be on the software side, where you need some kind of controller. However, the charger equipment also has requirements that's probably going to be a little bit higher. If you're doing AC out, you may need some kind of converter. If you're doing DC out, you need a bidirectional inverter. You probably need a sub-meter to measure electricity coming out. This can be expensive, right? So this can be on the order of a couple $1,000s. You may need some electrical equipment at your site to be upgraded. If your panel capacity isn't enough, you might need a transfer switch. So there's additional hardware upstream of the charging equipment that would be needed to enable bidirectional charging. And then you need like communications and grid integration equipment, network connection, probably most people have, maybe an aggregator platform. I'll talk about that in just a moment. So on the communication side, you need interoperability, right? So communication standards are needed to allow different parts of the system to talk to each other. You don't actually need a communication standards for this to work, but it's kind of necessary to have this at a larger scale. So an individual manufacturer could have a car that talks with a charger, that talks with your grid system, and they have their own proprietary design, but it would mean no other car could actually do it. And so the whole idea behind these communication standards is that it's like any charger, any car, as long as you're following these standards, you can do this V2G. So what sort of standards are there? So talking between the vehicle charger, or the communication between the vehicle and the charger, this is ISO 15118-2. This is the communications protocol that is being updated to allow for interoperability for V2G. It already exists as a standard, but doesn't cover, I would say, robustly V2G protocols. Between your charger and your network, There's a different communication protocol, OCPP 201. And then lastly, you might want a communications protocol between the charger and utility and like an aggregator service who's, let's say there's a company that wants to be in this space and they want a bunch of electric vehicles to participate in like a smart charging or V2G program. You need some kind of interface between the chargers and that aggregator. And so OpenADR is like one example of a communication standard to do this. Yeah, but most importantly, right, there's communication between the vehicle charger, the charger and your network, and then the network and your aggregator and utilities. Okay, so that's kind of how it would get set up on the consumer side of things. And then thinking about the benefits to the grid, right? The grid requesting help from the battery, that only comes into play based off of specific needs that the grid has. And so let's talk about what those needs are. So what are the problems that the grid needs help with? These are some of the value streams that folks talk about when you have something like smart charging or V2G. This is like where the money can actually get made. And so I'll kind of talk through these guys. So energy arbitrage. This is like I charge when it's cheap, and then I don't charge when it's expensive, or even I discharge electricity when it's expensive. Capacity value. So you avoid charging during times when there's a lot of demand for electricity. Ancillary services. This gets into some more nuances of the grid that we aren't really covering. But there are services besides just providing electricity. Frequency regulation, reserves, ramping flexibility. So there is value in certain assets on the grid in being able to respond quickly, okay? So think about the sun is going down and a bunch of solar power is coming off the grid. You need power plants to ramp up very quickly to provide electricity, and so there's actually more value for those power plants. And so that's one of the sort of value streams here. Renewables integration. So there's actually a case where we produce so much solar power that you actually have to turn some solar plants off. That's known as curtailment. And so you'd like to try and reduce that as much as possible. And then distribution deferral. I haven't talked about this as much, but think about some local neighborhood, a bunch of people start adopting electric vehicles, and then the utility has to come in and upgrade that like local transformer because it's overcapacity. That adds up to a lot of money. This is actually one of the biggest areas of cost for utilities and to our electricity rates. And so if you could, if in the same example, a bunch of people in your neighborhood adopt electric vehicles, but they can all switch off when they charge, then you may not actually need to upgrade that transformer, right? And so you avoid these local grid upgrades, and that can be a lot of value. So on the sort of research side, there's a whole bunch of work that's looked at all of these value streams. So, you know, energy arbitrage. There's a study out of Lawrence Berkeley National Lab. They looked at how participation can reduce electricity costs by 24%. They're saying EVs can make $250 a year on average in revenues just from energy arbitrage. There's a study out of Berkeley which has looked at renewables integration where they can reduce curtailment by 4 terawatt hours in a certain year. And potentially save on big costs in capital investments. On distribution side of things, this is a study that I actually did. with some grad students here, where we looked at impact on large distribution networks in California. And actually doing VGI, you could potentially help to mitigate $10 to $25 billion in more infrastructure deployment costs at the distribution level. Yes.
So, if electric vehicles are able to discharge during peak times and they become common, would it be possible that that could help reduce electricity prices since not only is demand lower, but like you're getting electricity back?
Yeah, absolutely. So actually this particular study we looked at, so there's this idea that like 10 to $25 billion in costs needed to upgrade all of the like distribution infrastructure, and the utility pays for that by increasing your rates. So this actually might cost money, but it's balanced out by additional load. So there's new electricity demand, which means that the utilities are making more money. So which one of those offset? And actually the load piece is larger, and so that actually drives electricity rates down. So adding load on the system, whether that's from like EVs or from like data centers and that sort of thing, I think a lot of people often hear about the cost associated with that because we have to install new transmission lines and put in all these transformers. And those costs are real and true, but also the fact that they are now paying for electricity, that if that load piece covers those infrastructure costs, then actually your electricity rates will go down. And so we actually looked at that explicitly here. We're saying over the next like 5 to 10 years, electric vehicles will probably depress electricity rates in PG&E by like, what was our number in PG&E? Something like 4 to 5 cents a kilowatt hour. So a little bit, but compared to what's kind of increased in the last couple of years, it's maybe relatively not as much. So the big thing that people are dealing with now with high electricity prices, that's changed. So our electricity prices have gone up like 50% every year for the last like 5 or 6 years now. That's why we pay so much for electricity in PG&E territory. That is not from electric vehicles. That's from wildfires. PG&E is taking the massive transmission lines that you see everywhere, and they're burying them. They're putting them underground, and that is a deterrent against causing wildfires. But it's also really, really expensive.
Didn't they start the wildfires with their lines recently?
So that's why they're burying them.
Wow.
Yeah, because what ended up happening was, okay, there's a huge slew of wildfires across California. PG&E was found liable for a lot of them. And yeah, in the courts, they were actually found liable, which means they had to pay for the damages caused by the wildfire, and they ended up going bankrupt. And so it changes the risk calculus for the utilities because they are now liable for incidents related to their electrical infrastructure. They want to be more risk averse and conservative with their equipment, so they are burying their transmission lines at enormous costs, and that is what's driving up our electricity rates. A little bit of an aside, but in case you were wondering why, I mean, it's that and some stuff related to rooftop solar, but yeah, that's maybe for a different class. Okay, so yeah, operationalizing this stuff is pretty hard. We have some idea of these like services that need to be provided, but how do we actually do it? And how do we realize those benefits, right? So one of the examples on the distribution side, so thinking about like at the neighborhood level, actually utilities don't really have insight at that level to provide signals to customers, right? Because we're talking about, oh, the way that you get a customer to respond is you say, oh, don't charge at certain times. Well, the utility may not know how to provide those signals because they don't get them themselves. As an energy aggregator, I may have difficulty guaranteeing availability of flexible resources, right? So this isn't like a battery that I just own that I can turn on and off, right? I have a bunch of people who are driving around in their cars and they want to participate in my program, and I'm like, oh, I need you to discharge your battery right now, or I need you to start charging your vehicle right now. And the participant's like, oh, sorry, I'm like driving my car, so I can't actually participate, right? And so the guarantee of the resource that the aggregator would rely on is, yeah, a little bit less clear when it's a car that's being used for other services. Yeah, and then some services will produce stress on the batteries, and so there's a lot of caveats to talk about here, but the idea is like, we've talked about battery degradation, right? And so if you take your car and you start participating in grid services, and the grid is like, okay, charge your car, okay, stop charging your car, okay, discharge your car, stop and charge your car, right? So you're cycling your battery a lot more, and there's a question of, okay, that actually leads to battery degradation. Is the money that I get paid for providing these services gonna like compensate for that enough? And so that's kind of open question. So with that one in particular, yeah, I actually have a little slide on that. So does battery degradation actually negate the benefits of participating? Probably not. So newer chemistries are a lot more resilient to degradation, right? We talked about how lithium iron phosphate is actually very resilient to degradation. Driving, it turns out, stresses out your batteries a lot more than the vehicle to grid participation and the speed at which they're discharging. There's kind of an easy way to think about this, right? If I have a 100 kilowatt hour battery and I'm charging at 6 kilowatts, okay, that's gonna take me like 15 to 20 hours to charge up the battery. If I'm driving on the road at freeway speeds, I'm probably gonna discharge the car in like 4 to 5 hours, right? So the speed of the discharge makes a difference with degradation, and driving is just generally more stressful for your battery. And then lastly, we have looked at real world data on battery degradation, and generally speaking, it's just not as bad as people have been expecting. So with this particular question, I think it's not as big of a deal. Okay, but so what's in it for customers? We don't pay all of these benefits that I'm talking about on the grid to customers on that like same one-to-one basis, right? So we have to think about designing programs that, one, are actually attractive enough for customers to join, two, will retain customers in the program long-term, and then will, in the aggregate, align what we pay out to customers to the grid benefits. So this is still a very nascent area. There's over 140 pilot programs for smart charging, and about 20-ish vehicle-to-grid pilot programs that have been deployed or are currently being run across the country. And they are looking at all sorts of design elements for different programs. And so like enrollment cash, if I do recurring payments, flexibility is actually a really big one for design. So this is like, oh, not only will I give you money to participate, I'm gonna give you some flexibility. You can say, you can have some number of override days. So for example, let's say I participate in the program, and then they get to control the charging and discharging of my vehicle, but I know that tomorrow I need to drive down to SoCal. I want my car to be really charged up, so I can override their control. So giving people override days is really important. You can have like minimum thresholds. So something like, oh, you can control the charging and discharging as you like, but you got to make sure tomorrow morning I'm at least 85% charge or 90% charge. You can have these guaranteed thresholds where you say, you can charge and discharge my battery, but please don't go below 40% or 50%, right? So there's interesting aspects of the program design. And we've done some work to look at how those flexibilities affect people's enrollment. Yeah?
Does this be at like every charger, or could you just go to a different charger like somewhere else if you want to make sure that your car gets charged on the...
Yeah, so this, I think generally these programs are targeted at like home charging, and so this would really be just for home charging. And then you could always override it if you needed to charge, or yeah, you could go somewhere else. Yeah. Yeah, so this is work that we've done that looked at enrollment rates. There's actually another paper out of some economists at UC Davis who published, and they actually came up with very, very different numbers from what this study did. So definitely still an open area of study. And for the customers, this was a study we looked at potentially what you could generate in value, and we actually found you could get thousands of dollars out of this a year. That's kind of on the optimistic end of things, but there's a bunch of studies that have looked at this as well. Okay. Yeah, I have a couple more slides that I'm going to skip over. You guys can look at this at your own leisure if you're interested. These are just some barriers and policy issues in this space. So I'll just conclude, a couple takeaways. So emissions depends on the grid, where you are, and when you charge can shift the answer. EVs are a massive flexible resource, and someone's going to capture that economic value at some point. So I would expect V1G and V2G as kind of an inevitability. The value streams are real but fragmented, so someone has to figure out the best ways to capture that value, and operationalizing it is hard. Okay, we'll end here for today, and see you guys next week on Monday.